Okay, for this practice problem here, we're going to start with the chemical formula, H2O, and go through all of the processes. We're going to draw the Lewis dot structure and then go through and count the number of electron domains, use that to predict the shape, use the shape to predict the polarity, and use the polarity to predict the intermolecular forces. So the first thing we need to do is count the total number of valence electrons in H2O. And H2O has 2 hydrogen and 1 oxygen. Each hydrogen has 1 valence electron, and oxygen has 6, and I know that from its location on the periodic table. So the total number of valence electrons that water can have is 8. So now I go ahead and I go to step 2, which is drawing the molecule, picking the central atom. Hydrogen can never be the central atom, so the central atom is going to wind up being oxygen. And then hydrogen will have to be the 2 atoms on either side. Okay, so now I move on to step 3, which is to subtract. Subtract the electrons that I just used to make the bonds. Every time I make a bond, I use 2 electrons. So since I made 2 bonds, I used 4 electrons, which means I have 4 electrons left over. Step 4 says that I'm going to use the electrons left over to complete the octet of the outside atoms, which in this case is hydrogen. But hydrogen's pretty special because it's so small it actually only needs 2 electrons to be stable. So I don't need to add dots around the hydrogen on the outside. If on the outside was chlorine or fluorine, yep, I would need to put dots around that. But since it's hydrogen, I don't. So now I move on to step 5, which is completing the octet of the central atom. So I put dots, which stand for electrons, around that central atom. And I used 4, so now I have no electrons left over. And that means I may be done. If I have no electrons left over and every atom has a full octet, or hydrogen only has 2, then I'm done. So it looks like I'm done with this molecule because every atom has a full octet. I've used up all my electrons. So now I count the number of electron domains. And an electron domain is a bond or a lone pair. So if I look around hydrogen, or excuse me, I look around oxygen, right? If I make a box around oxygen, there's 4 sides to the box. And how many of those 4 sides are there electrons? 4. So that means that it has 4 electron domains. So if a molecule has 4 electron domains, it could be one of 3 shapes. It could be tetrahedral, it could be trigonal pyramidal, or it could be bent. And that's based on the number of lone pairs. So we have a table, and if I look on the table, I see 4 electron domains with 2 bonds and 2 lone pairs. The name of that shape is bent. Now I look at polarity. Molecules are polar if they have lone pairs on the central atom, or if the outside atoms are not all the same. So water does have lone pairs on the central atom, so it is polar. And then when I'm choosing the intermolecular force, it can either be hydrogen bonding, dipole-dipole, or London dispersion forces. If the molecule is nonpolar, the only type of intermolecular forces it has are London dispersion forces. So that's not this case. If the molecule is polar, like water, it could be dipole-dipole or hydrogen bonding. How do I know which one is which? Well, hydrogen bonding is the intermolecular force when hydrogen is bonded to the 3 most electronegative elements: fluorine, nitrogen, or oxygen. And in this case, yeah, there's hydrogen-oxygen bonds in this. So the intermolecular forces would be hydrogen bonding.